morning to everybody, and thank you to the organizing committee. Today I'm going to talk about a work that I have done in collaboration with my colleague at CNR, Institute of Microelectronics and Microsystems in Agrate, Brianza, Italy. The topic of the work that I'm going to present is semiconducting qubit, and in particular this is a theoretical work in which we investigated the dynamical behavior of this particular qubit system that now I'm going to present when magnetic and charge noises are considered. Okay, the first question is why we study this kind of system. The answer is that we believe that the confinement of electron spins in a solid-state architecture is a very rich platform for quantum computation. This is witnessed by several works by several groups in the world that work on this topic. And with confinement, I mean both the confinement through donor in host materials, for example, phosphorus in silicon is maybe the best known, but also confinement through quantum dot that can be built through heterostructures, but also through gate potential. And so we talk with electrostatically defined quantum dot. But of course, in reality, the qubit live in an environment, and this environment can destroy all of these nice properties that are very interesting for quantum computation. And this causes the coherence, and this is evident when the fidelity of the quantum gate decreases due to this interference effect. The two main sources of the coherence that we consider and that we study in this work can be classified in two types. On one side, the magnetic noise that is due, for example, to the interaction with the nuclear spin in the host materials, so the Overhauser field of the host in the qubit. But also on the fluctuation on the applied magnetic field that are used in some architecture to manipulate the qubit. On the other side, we have also some kind of electrical noise that is due to charge fluctuation on impurities that are present in the, for example, in the interfaces, and act as traps for the charge. In addition, also the fluctuation in the electrostatical gates that are adopted to confine the electrons can cause the coherence. In particular, now we study the double dot exchange only qubit, and we study the dynamical behavior as if the control parameter is fixed, and so we call the always-on configuration. And now I will explain specifically what I mean. Okay, the qubit that we study is here represented in two figures. On the right side, I have put a sketch, so a paint of the double dot with the energy level that we consider, and I indicated the exchange coupling that interact between the electrons. On the right side, there is real images of work of some years ago, in which you can see explicitly the formation of the double dot with the electrons inside and all the gate used to manipulate this kind of qubit. This qubit was introduced by the group of Wisconsin some years ago in 2012, and then we have worked a lot on this on the theoretical analysis on this qubit, first of all, deriving an effective Hamiltonian model that describes the interaction of these three electron spins confined in a two dot. In particular, the important point is that starting from an Hubbard-like model, of course very complicated for three interacting electrons, we have obtained simply a sum of exchange coupling in which all the coupling contain all the information about the physics of the system and the parameters, of course. If you are interested in this, you can see our previous work that here I cited. The logical basis that this qubit used is defined here as a combination of a single and triple state of the couple of spin in one dot with the spin up or down of the single electron spins in the other. And here is a representation of the effective Hamiltonian model in this logical basis. The main advantage of this qubit with respect to others quantum dot qubit is that the manipulation here is doing only by electrical voltages. So we don't need microwave, we don't need magnetic field, but only changing the tunneling and acting on J1 and J2, we can manipulate and do all the operation that we want. We have also derived, for example, the sequences that realize 1 qubit and 2 qubit operation. But the point of this work is to study exactly the dynamic of the system, and thanks to the compact form of the effective Hamiltonian model, we are able to write the evolution operator also in a compact analytical form, using the Cayley-Hamilton theorem. So we can write the evolution operator as a polynomial of order n minus 1. And finally, substantially, we can obtain the dynamics through this last formula, in which appears only some coefficient that depends on the eigenvalues of the operators minus e times h, and the effective Hamiltonian model and the identity operator. How can we add noise to this system? The idea is to consider the noise, the magnetic and the electrical noise, as Gaussian distributions, and evaluate the noise changing the deviation standard of this Gaussian distribution. P is the probability starting from an arbitrary initial condition to find the qubit in the condition that we have prepared when the times go on. And we calculate what is called on the left-hand side of this equation disorder average probability, integrating over all these three sorts of noise that we consider in this qubit. Just to clarify this point, we consider a specific initial condition of interest also for experimental purpose, because we consider to prepare our qubit in the zero logical state. In absence of noise, when the times go on, the probability of finding the system in the zero logical state is simply an oscillatory function in which all the coefficients depend, of course, on the coupling and on the parameter of the system that I showed you before. And in some cases, it is possible also to see the complete Rabi oscillation between 0 and 1 of our system in definitive for a time that is infinite, of course. But when the noise is added, it's not true that the oscillation it's forever. And what happens is that this oscillation becomes to decay. In this plot, I represent some result that we have obtained solving the integration that I showed you before, in which are varied the sigma E or sigma J, the variance of the Gaussians, or vice versa. And as you can see, with respect to the zero noise case in which the oscillation are forever, what happens when noise is added, as expected, of course, is that the amplitude of the oscillation becomes to decrease and go to a steady state values. These plots are all done in function of a normalized unit that is J0 times T. So this approach is valid whatever is the physical system that we have. And so once that we have specified this value of J0, we can have a physical time in seconds, for example. And I have, in fact, put another horizontal x-axis in the upper part, as you can see in all this plot, in which I fixed this value of J0 equal to 1 microelectron volt. That is one typical value for the qubit system that we study in silicon. And as you can see, here we can have an estimation in second of which is this dephasing time of the disorder average probability. The next step is to have an estimation of the coherence time from this calculation. And what we have done is to follow an approach that is already presented in previous work by the group of Dasarma in the recent years, last years. And what we have done is substantially to do an envelope fitting procedure. This means that once that we have looked at the disorder of average probability in the different space of sigma E and sigma J, we consider the envelope upper curve of all this probability, and then fit this curve with the equation that you see in the upper part of the slide. In this way, you can have an estimation of these T2 stars, that is the coherence time that in which we are interested for the quantum computation application that I say you in the introduction. And in this way, we can extract this value for all the value that we have considered in sigma E and sigma J. Just to have analogous images in this two-dimensional plot, I report also the quality factor that maybe can have a direct impact on the coherence time, because when T2 stars go to infinities, the quality factor is equal to 1, and we are exactly in this region of the plot in which the noise is 0. And then when we go farther from this point, we can see that the quality factor becomes, of course, worse. Now the point is, we want to study a physical situation, so we want to have an estimation of the coherence time in seconds, for example. And so in this plot, I collect all the results just to present you what happens when we consider a qubit a real qubit, so not in normalized unit. In this case, J0 is equal to 1 microelectron volt. Just we are talking of a coherence time that can reach 100 of nanoseconds. In addition, these two vertical line marks a typical value for the minimum magnetic noise variances in gallium arsenide and in silicon. And as you can see, we have greater coherence time in silicon with respect to gallium arsenide, of course. The other point is what happens if we consider different initial conditions, for example. So up to now, I have to show you the initial condition with the qubit in the zero logical state. Here, I compare this initial condition with another one represented by empty circles in the plot, in which I consider a linear superposition of 0 and 1 logical state. As you can see, the two curves are very near each other, so it does not depend very much on the initial condition that we study, but it's very different for the material of the qubit that we are analyzing, because, for example, in blue we have gallium arsenide, that is the worst case, and then we have natural silicon in green, and the 28 silicon in red, that is the nuclear-free isotope material, so the one with ideally has 0 magnetic noise. So the one to prefer when we do quantum computation in silicon devices. So just to conclude, the main point that I want to stress is that the double dot exchange only qubit is a very fruitful qubit in quantum computation due to its fast manipulation and its electrical control. We have studied the influence of environmental noise considering the disorder average probability in a large range of value for sigma E and sigma J. And we have given also an estimation of the coherence time that is useful when we want to study then the gate operation, 1 and 2 qubit, of course. The conclusion that we have is that this qubit is more sensitive to electrical noise than magnetic noise, and that the qubit in silicon outperform gallium arsenide qubit in terms of noise resilience. Moreover, when when the electrical noise is sufficiently small, we can also see an improvement of silicon-28 with respect to silicon. Of course, semiconducting materials has also a great importance relating to the integration with this qubit with the present existing microelectronic industry. And so for this reason, we believe that this is a good starting point to develop this kind of qubit. I wish to thank the European project Mosquito and all of you for the attention.